Hello again. This is Math 2233 coming to you from the College of DuPage, and the title of this lecture is Implicit Differentiation, Gradients, and Directional Derivatives. As always, please be an active learner as you watch this video. The chain rule can be used to give us a better way, a more efficient way to do implicit differentiation. Let's talk about this. Suppose we have an equation of the form capital F of xy equals 0. It could be any constant, but let's just say equal to 0, which defines y implicitly as a differentiable function of x. That is, y does equal f of x, and this equation really looks like capital F x comma f of x equals 0. For all x in the domain of lowercase f. Now, if capital F is differentiable, then we can use the chain rule to differentiate both sides of this capital F of xy equals 0. And on this side, the derivative of 0 is 0, of course. On the other side, I get this. This is the partial of f with respect to partial of capital F with respect to x times the derivative of x with respect to x plus the partial of capital F of a y times the derivative of y with respect to x, and that's equal to 0. Now, this is 1, and if this number here is not equal to 0, we can actually solve for dy dx in much the way we did before. So if we solve, we would put this number on the other side. It would be negative, and we divide by this, and so we obtain this result. Dy dx is equal to the negative of the partial of capital F with respect to x divided by the partial of capital F with respect to y, or written in a more compact form this way, minus f sub x over f sub y. Now, this function can be derived using what is called the implicit function theorem, which is some math that's proved in advanced calculus courses, or perhaps a real analysis course. And that gives conditions under which that assumption is true. And the assumption is that y is a function of x, at least in some neighborhood of the value x. And the implicit function then states that if capital F is defined in a disk containing AB, and this is equal to 0 at the point AB, and the partial with respect to y does not equal to 0, then both capital F of x and capital F of y, and those are not of, these are sub, these are derivatives. This is the derivative of capital F with respect to x, and the derivative of capital F with respect to y are continuous. Then this equation defines y as a function of x near the point, and the derivative is given by this equation up here. Now let's apply that, please, to this problem. You want to find y prime if you have it defined implicitly this way. So this is x cubed plus y cubed is equal to 6xy. You know what to do. Let's see how you did. Okay, so we're going to use this formula, so we need to calculate the partial of capital F with respect to x. That's going to be 3x squared minus 6y. And notice that we did move this over, so this is actually equal to 0, so we reconfigured that as well. And so we get this as the numerator. And the denominator similarly, because of the symmetry, is going to be 3y squared minus 6x. We put the negative there, and then we simplify. We have a factor of 3 that can be divided from numerator and denominator. So the answer is dy dx is equal to this expression. Make sure you can do problems like this as we go forward. Okay, now suppose z, we're moving up in dimension, is given implicitly as a function z is equal to f of xy by an equation of the form capital F of, now it is xyz is equal to 0. Well, that means, of course, that if we're assuming this an implicit function, that z is f of xy, so this is capital F of xy, and that is lowercase f of xy is equal to 0. Then we're going to use the chain rule again. So we have the partial of f with respect to x, dx. This is the partial of f with respect to y, dy dx. And this is the partial of f with respect to z, and this is dz dx. And again, all those are partial derivatives because we're in higher dimensions. But this partial is 1, and this one is 0. So the equation again reduces to this, and we can solve for dz x or y, and so we can solve this equation, and we obtain one of these equations or the other equation depending on which way we're taking the derivative. So you see the same formula works if you have a regular derivative in 2 dimensions or partial derivatives in 3 dimensions or even higher. And again, this is the implicit function theorem that states all of this is true. So these again are formulas you want to commit to memory and be able to use. Okay, so here is a problem. We want to find the partial with respect to z and the partial with respect to y if you have this implicit function, and notice that this is equal to 1, so you want to move it over to the other side. You know what to do. Let's see how you did. Okay, so you just apply the formulas that we have, and you should get these results. Make sure that your calculations match up with the ones that are given here. Now we're going to use these ideas of implicit differentiation all along the way. Now we're turning our attention to a different concept, and we're going to talk about directional derivatives, and eventually we're going to talk about the gradient vector. So let's talk a little bit about what happens here. So the weather map that's shown down here, we have a contour map showing isotemperatures or isothermals, where you have the same temperature. So everywhere here that is 50. If you go down here, it starts being 80, and then it's 70 here, and so on and so forth. So you have the changes in temperatures. The partial derivative T x at a location such as Reno is the rate of change of the temperature with respect to the distance we travel directly east. So we'd be here. So how does the temperature change as we go directly east, which is in the positive x direction? Similarly, Ty would be if we're going south from Reno. And we could also go T positive Y, and that's going north. Actually, we would be going negative if we were going down there. So we end up talking about the partial of T with respect to Y. But suppose we want to know the rate of change when we travel southeast from Reno to perhaps north Las Vegas, and that's a different direction. So how do things change along this line? Not along the x direction or along the y direction, but in a different direction. This is the concept of the different kind of derivative called a directional derivative, which enables us to find the rate of change of a function in 2 or more variables in any direction. Okay, so here's how we go about it. So we take z equal f of xy, and then the partial derivatives are these. And what we're going to do is we're going to use the same idea, except instead of moving just in the x direction or just in the y direction, what we're going to move is in a general direction. Okay, so now let's go down here and we'll talk more specifically about the directional derivatives, because these are special cases of the directional derivatives. So suppose that we now wish to find the rate of change of z at a point x0, y0, and that's a point on the surface, so it's right here in the picture, and we want to find this in a direction of an arbitrary unit vector, and this is pointy bracket AB. Now you realize, and this is the figure up here, so pointy bracket AB, which really could be the cosine or the sine, and this really should be of cosine theta, sine theta. It really shouldn't say well, I guess we could talk about u. This is the magnitude of u, but we could also talk about it in this context being a unit vector. Now, it is important we're talking about a unit vector because we really don't want the magnitude of the vector to determine something. We really just want the direction that it's pointing. And you recall a unit vector tells you the direction that we're pointing. Okay, so we want to be in the direction of an arbitrary unit vector, which is pointing bracket AB. Okay, so you consider the surface, and so here is the surface that we're on, and there is the point, and so this direction right here is in fact the direction of the unit vector evaluated at that point. And so you see what happens is that the point P, x0, y0, 0 lies on the surface, and the vertical plane that passes through this in the direction of u, the direction of the vector, intersects this in a curve, and that's the slope of the tangent line to the curve. So the slope of the tangent line, t, to c, at the point P is the rate of change of z in the direction of u. Ponder this a bit as you go forward. Now, why would you use this? Well, there's a whole bunch of different examples. And recall, the directional derivative gives you the rate of change of function in a particular direction. And this can be used to find the direction of greatest change. We'll do that later. The direction of zero change, or many other quantities. So, here are three examples. Aeronautical engineers design missiles that have heat-based guidance systems. Such a missile would attempt to follow the direction of greatest temperature change. To do this, it finds the direction that produces the greatest directional derivative. Another application to geosciences. The depth of a lake varies across the surface of the lake, and that surface is underground, of course. A hydrologist measures this to monitor environmental change. The depth varies differently when moving in different directions. The bottom is not flat. So this is done by calculating directional derivatives. And in electromagnetism and other fields, astronomers, as example, often consider the magnitude of magnetic fields. This can be modeled using a real valued function, and you can see that the magnitude, north and south, these are the lines of gravitational attraction from the north and south poles. So the directional derivative tells the astronomer how the magnetic field's magnitude changes as you go in certain directions. So how do we find then the directional derivative? And there's the definition. So the directional derivative of f, a function, at x0, y0 in the direction of a unit vector, u equal pointing bracket ab, is given by this. So you see, and this is the notation. So this is the directional derivative of f at a point in the direction of u is given by, and you see instead of going along the axis, x goes in the direction of magnitude a, and in y you're going magnitude of b because the vector is, and again this is a unit vector, is pointing bracket ab. So it's this limit if this limit exists. Now, as so often happens, we want to know the limit definition as a concept, but we have other more practical ways of calculating it. That will be true here as well. Now, what would be examples where you use this? And you're interested in the rate of change of a measurement, such as air pressure, rock density, and altitude. It depends on the path that you travel, and thus we need a directional derivative for its computation. So, as a rover on Mars, this is very timely right now, travels in a particular direction, how do the atmospheric and geographic conditions change? To compute the answer, they compute a directional derivative. Geologists and those who analyze geography measure the changes in density in the ground with a directional derivative. This helps to find the best path to drill for oil. And last but not least, directional derivatives are used in the optimization calculations made by rescue robots or robots on Mars, for that example, which are designed to find people or other Martian probes or aliens that are trapped in collapsed structure using the quickest and safest path possible. Okay, so if we compare the definitions 1 and 2, we do see that if we're going in the x direction, u would be I, 1, 0, and j, 0, 1 would be in the j direction. So again, the partial derivatives are special cases of a directional derivative. But here is a problem I would like for you to consider. Look at this map, and again, you're just estimating, but estimate the value of the directional derivative of the temperature function at Reno pointing in a southeasterly direction. You know what to do. And we'll look at the solution to this when we return. But for now, more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. May God bless you all.